All right, guys, I'm going to start every day right here. Remember, this is the 5 ways that we can quantify delta H. Yesterday, we looked at stoichiometry. I think you pretty much got that. That wasn't difficult at all. We started calorimetry. And so the one thing that I want to go back and I want to look at is this calorimetry part. And the problem that we left off yesterday with was the problem. Dang it, I forgot to put the slide on there because I added a slide yesterday afternoon. Was this problem right here. This was the last question on last year's exam. And I told you, I said, I'm going to be honest with you, I had no clue how to do this. Even when I saw it, once they released the test, I said, I don't know what they're doing. I don't know how in the world they got the answer to this question. And so let's kind of talk about it. And I showed you how this was yesterday. Remember, whenever we do the specific heat capacity formula, it's Q equals M CP delta T. All right. Well, this is, again, and I wrote this yesterday, this is mass, this is specific heat, and then obviously you guys know what delta T is. But the formula that they used was a little bit different. They used N times capital C times delta T. You already know what N is. What is N? This is moles. Capital C is molar heat capacity, and delta T is the exact same thing. And so, like I said, until last year, I had no idea that this formula was even real. It was one of those things that you don't do it, and so you don't understand that it exists. So if we go back and we focus on this, which is N times capital C times delta T. Go ahead. Can we go back to that? Okay, sorry. N, which is moles, times capital C, which is molar heat capacity, times delta T, which is almost the same thing, except instead of using mass, we're using moles, and instead of using specific heat, we're using molar heat, and the values are a little bit different. So my heater's always running. Colby, what? Did you really, Colby? Okay. Shh. Okay, here we go. So if we look at it, now, the way, I don't like how they have it arranged, but again, it doesn't matter how you have it arranged. That's just how they have it. So in the problem, they tell you that right here. It says the molar heat capacity is 24 joules per mole. And if you look right here, what is that? So this right here is your capital C. 1 mole, and it tells you needed to purify 1 mole of aluminum. So there's your N. And then where in the world did this 635 come from? It's your change in temperature. And here's where it gets weird. It says it was originally at 298 Kelvin. And then it says the melting point of aluminum is what? 933. So to get the aluminum to the point where it would melt, you had to change it 635 degrees. Does that make sense? So that's where the 635 came from. And so you had to actually do that math as well. And so then they give you 15,000 and then they convert it to just 15 kilojoules. So here's the deal. You got 1 point is earned for calculating the amount of heat needed to raise the temperature to 933 degrees Kelvin. Reread that. You get 1 point for calculating the what? Amount of heat, which is 15 kilojoules or 15,000 joules. So here's the deal. What are we trying to do? Let's think about this in terms of a realistic approach. We're trying to purify aluminum by doing what? By melting it. So do you agree that before we ever do anything, we've got to melt it? Right? All right. So if we melt it, it takes 15,000 joules from room temperature to the melting point, right? Now, is that purifying at all? No, that's just melting it. Does that make sense? Okay. Well, then keep reading. And then it says the heat of fusion of aluminum is 10.7. What is heat of fusion? Well, let me ask you something. If you melt something, what is the melting process? Solid to a liquid. What is fusion? So we're trying to melt it down, get all the aluminum, and then once it's in the liquid form, what are we trying to do? Put it back together. So the 15,000 is just for what? We're just trying to melt it. But the question asks us to not only melt it, but it also asks us to do what? Fuse it back together. Well, so this is where this part comes from. So it takes 15 kilojoules to melt it. And then, to purify it, we need to add an additional 10.7 to do what? Fuse it back together. So this is melting plus fusion. That's where they get the 26 kilojoules from. I agree with you, and that's why I hate this question. I absolutely agree with you. And that's why this was a very, very, very low point question. It's only worth 4 points, and I don't think it was a very fair question at all. It's a calorimetry question, but it's not very calorimetric. You get me? Okay. All right, go ahead. You could do that, either one. So you could say 15,000 joules and 10,700 joules and come up with 26,000 joules. Yes, but here's the problem you're going to run into. Mary, does that make sense? You sure? What'd I just say? That's what I thought. Okay. So the equation for the overall process of extracting aluminum from aluminum oxide. Now, we want to purify aluminum, right? But it's not in pure aluminum form. It's in this oxide. So what are you going to have to do to this aluminum oxide? We've got to get it out somehow. Which requires, so here's the question. Which requires less energy? The recycling of existing aluminum. How much energy did it take to recycle aluminum? 26 kilojoules. Or extracting aluminum from the aluminum oxide. Justify your answers with the calculation. And then it gives you this thing, and it tells you the aluminum oxide, first of all, is it an endothermic or exothermic reaction? How do you know it's endo? It's positive, okay? This is the stoichiometry version. So this is the reason why I'm showing you this problem. Do you agree that, and again, you don't have to write this unless you want to, but this problem was a calorimetry problem, and this problem is a stoich problem. So do you agree that you're calculating delta H in two different ways? Yep, and these are the two that we're covering. That's why I'm showing you these now. So you have 1,675 kilojoules per mole of reaction. And notice what it does. You have 2 moles of aluminum for every 1 mole of reaction. How do you know that statement right there? Okay, so when you have Al2O3, for every one of these compounds, how many aluminums do you have? 2. That's where it comes from, the subscript. Okay, the subscript. So you get 837.5 kilojoules per mole of reaction. So if you notice what it says, so 1 mole of aluminum took 26 kilojoules to purify, but it took 837 kilojoules to extract. So which one requires less energy? The purification, the recycling process. And like I said, I don't like this question, but it is what it is. Go ahead. It's okay. Yeah, you can do that. It's fine. No big deal. So here's, if you want to, what I'll do is you can take a picture of that and you can put it in instead of writing it all down. That may probably be the best method of doing this if you're on the iPad. I'll pause it, let you take a picture of it. Well, if you would take so many selfies, it wouldn't always be on your face mode. Whatever happened to, like, mirror pics? All right, so again, one more time. This is going to be the specific heat formula that we're going to use. Again, please don't forget, and that's why I'm glad I saw that question, is because there's also something called molar heat. But if it's molar heat, do you use M or N? N. Very good. Okay. Same thing. Everything else can be found. So, say it again. Nope. I don't think so. Do they? Is it on there? It is on there, yeah. It's Q equals MC delta T. And then over there on the right-hand side, it says C is specific heat capacity. And that's why I don't like that problem. That was molar heat capacity. And that's why I didn't think it was a very fair question. But it is what it is. Yes. You want to do it? Can we do it at the very end, please? Okay. Now, again, I'm going to go ahead and forewarn you guys. This number you have to have memorized. You cannot get anywhere outside of this number. If you ever do anything with calorimetry, you've got to have that number memorized. The specific heat of water is 4.18 joules per gram degree Celsius. Now, this other number, what is 1 calorie per gram degree Celsius? Same thing. So remember whenever we had the bomb calorimeter, if you're trying to find the calories, do you agree that it's a much easier calculation if you plug a 1 in than you plug in a 4.18? It makes the calculations a lot easier. So if you're finding the Q of a calorimetry constant, it's a lot simpler math. But they don't use calories, they use joules. Yes? Yes, that's exactly right. Every gram of water that you intake has a calorie of energy. Huh? No, but you still have to burn it. But you got to remember, that's a little different than real calories. Those are kilos. Exactly, they're kilocalories, so it's 1,000 calories. If you want to break water down to get it out of the body, does it have to go through a chemical process? Yes, and it's going to be at least 1 calorie to break it down, which is 1,000 regular calories. Okay, all right. Yes, very good. So if you notice right here, this is the two things that I want to point out is, notice that. What takes more energy to increase the temperature, liquid water or solid water? Liquid water. So it's taking more and more energy to change it. So water has one of the highest specific heats known. This property makes life on Earth possible and regulates the Earth's temperature year-round. So it's important to understand that. And again, we see this one more time. So whenever you calculate Q, what are you actually taking Q of? Remember, where's the thermometer in? The thermometer's in the water, but what is the question asking you for? The Q of the reaction, right? So how are the Q of the water and the Q of the reaction related? Equal, but opposite. And I'm telling you now, that's going to get you on some of these questions that we're going to go through, okay? Units of energy, you've got the calorie, which is the amount of heat needed to raise the temperature, 1 gram of water, 1 degree Celsius. The kilocalorie is the food calorie with a capital C. The joule is the one we're knowing. And I'll go ahead and tell you, we're probably going to run into a few of these, but just know that 1 calorie is 4.18 joules. Do you recognize that number? Yep, that's the specific heat of water. Yes, that's why calorie is 1 and joules is 4.18. Okay, and then a kilojoule is 1,000 joules, which you already know that. All right, so here is our first calorimetry problem. In a coffee cup calorimeter. Now, why do they not say bomb calorimeter? It's too expensive. Just like if you're running a platinum and graphite, same concept. Okay, 100 milliliters of a 1 molar sodium hydroxide and 100 milliliters of a 1 molar hydrochloric acid are mixed. Now, let's talk about the chemistry of this. First of all, what is NaOH? What kind of base? Strong base. And what is HCl? A strong acid. Hydrochloric acid, strong acid. I'm going way back, and you've got to pull this from back here. If it's net ionic, if it's strong, what did you write? If it was strong, what did you write for net ionic? You wrote the ion. What's the ion for a strong acid? H plus. What's the strong for a base? OH minus. So what is the net ionic equation for an acid-base reaction? Hydrogen ion plus hydroxide ion equals water. Okay, just want to throw that back at you. Both solutions were originally at 24.6 degrees Celsius. Do you agree that it's important that they told you originally and a temperature? Yep. After the reaction, the final temperature is 31.3. So from those two numbers, what can you get? You can get delta T. Assuming that all solutions have a density of 1 gram per cubic centimeter and a specific heat capacity of this. Now, why can we say that the specific heat capacity of both solutions is equal to this? Say it again. It's equal to water. If you have aqueous solutions, what has to be present? Water. It's not going to change the specific heat a whole lot. calculate the enthalpy change for the neutralization of HCl by NaOH. Assume that no heat is lost to the surroundings of the calorimeter. So let me ask you one thing. Read the question again. What is the question in this entire paragraph? Calculate the enthalpy change. What is enthalpy change? So they're asking you to calculate delta H. Do you agree? But the problem is they gave you specific heat, they gave you delta T, and they gave you some solution numbers. So what formula are you going to have to use? Q equals MCP delta T. But here's the problem. What did the question ask you for? Delta H. The formula you're going to have to use has no delta H in it. So how do you get from Q to delta H? When are Q and H equal? At constant volumes and constant pressures. And that's exactly what's going to happen in this calorimeter, right? Does that make sense? It's because the volume's not going to change. Very good. The delta V is going to stay the same. So I'm going to change pages, and I'm going to have to help you, let you help me through this. So here's the deal. So we've got Q equals MCP delta T. So the first thing, I'm going to spread this out a little bit. Q, I'll come back to this. It told you the CP was 4.184 joules over gram. Was it degree Kelvin or Celsius? Yeah. Okay. So delta T. When you're doing delta, is that initial minus final or final minus initial? Which is, what was the final temperature? 31.3 degrees Celsius minus what? 24.6 degrees Celsius. This is for Nick and Mitchell. At some point in your calculations, do you need to show that thing? Yes. Okay. You don't have to plug it in like that, but somewhere in your work, somewhere in this question, you need to show the delta T. Okay. You can plug it in just like that, or you can do it however you want to do it. Okay. It does not matter. So here's the problem. This is the thing that's going to get us. Okay. Everybody got that? Can I change pages? It's joules over grams times degrees Celsius. Okay? So here's the problem. They tell us that we have NaOH, and they tell us we have 100 milliliters and 1 molar, right? Then they tell us we have HCl, and that's 100 milliliters and 1 molar. I need what to plug back into my specific heat calculation? I need mass. I've got volumes, and I've got concentrations. Very good, Nick. They gave you a density, and it tells you assume the density is what? 1 gram per milliliter. So, how do you get the mass out of this thing? Okay? So, if we do the density triangle, what is density equal to? Density is equal to mass divided by volume. Right? Well, the problem is, it told you the density was what again? 1 gram what? Read the problem. So it said what? Gram per what? What did I tell you yesterday? 1 cubic centimeter is equal to 1 milliliter. So they're the exact same. That's why I'm going through this, is to make sure that you're connecting on all these things. So if it told you the density was 1, well, we can plug a 1 in here, 1 gram per milliliter. What was the volume? 100. Hold that thought. Hold that thought. So, what's our mass? 100. So the mass is going to be 100. But here's the deal, and you said it right. That's the mass for which one? Both of them. So they both have a mass of 100 grams. No, I'm going through the steps of this. Okay. So what's your total mass? 200 grams. So that's what will be plugged back into M. Here's the part where students get messed up. What's the one number up here that can throw this entire problem for a tailspin? That number. Because what if the density's 0.75? You got to change your masses, right? The other thing is, what if it told you it was 1 liter of each solution? Okay, that's the problem, because whenever we did this yesterday, I told you that 1 gram was equal to 1 what volume unit? Milliliter. And so if they gave it to you in liters, it's going to be in the thousands range. You got to make sure you catch that as well. Okay, so coming back here, we know it's 200 grams. Okay, real quick, what is the delta T? 6.7 degrees Celsius. Okay, so then it just turns into a simple multiplication problem. Do you agree there's a lot going on in this problem, though? Once you get it in this, it's easy. But getting it in this is the issue. Now, the last thing that I want to ask you, the Q that we're solving for, where's the thermometer? And what is water? It's a solution, right? So we're calculating the solution. So what is your Q of the solution? What's the number? I guess is my question. Let's go with, actually, let's look at the problem. So I've got 4, I didn't need that number, 3, 4, let's go with 3 sig figs. That right there? Okay. Mitchell, do you agree that units are very important here? Yeah, because if you didn't know, what happens to your grams? Grams cancels, what else cancels? Celsius cancels, leaving me with joules. Okay, so I've got 5,610 joules. But again, here's the part where every year students mess up. They circle that answer and they move on to the next question. Go back and reread the question one more time. The question was, calculate the what? Enthalpy change for the. And here's the question. What is that? That's a reaction, correct? So down here in green, we said the Q of the calorimeter is equal to negative Q of the reaction. So you told me that the Q, the solution, which again is what? The water, right? Was 5,000, what did you say? 610? Okay, I forgot the hundreds place. So 610 joules, which means the Q of the reaction is equal to negative 5,610 joules. And so that is your final answer. You could. So if you, I guess the final answer would be delta H of the neutralization is negative, 5.61 kilojoules per what? Per mole of reaction. Yes, anytime you calculate delta H, it has to be per mole of reaction. So here's my question. Is this an exothermic or endothermic reaction? Exo. Anytime you mix an acid and a base, it's going to give off a lot of heat. A lot of heat. Because those are dangerous reactions. Same exact thing. That's true. It does get cold. So strong and strong gets hot. Negative 5.61 kilojoules per mole of reaction. Oh, NEUT, neutralization. My bad. No. You don't. Alright, so see if you can do this one. See if you can figure this one all out on your own. What? Alright, so Jacob, you said it right off bat. That second word in the entire problem was what? 1 liter. As soon as you saw that, there was hopefully a red flag kind of went off, and I preluded to that in the previous problem. But when 1 liter of a 1 molar barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of 1 molar of sodium sulfate solution at 25 in the calorimeter, the white solid barium sulfate forms as the temperature of the mixture increases. And I'm pulling way back here again, and again, I want to kind of stop. If you were to write the net ionic equation from this, what 2 ions would you have to get rid of in order for the net ionic equation to be true? Okay, what do we know about all nitrates? They're soluble, and what do you know about all group 1s? They're soluble. So what it would be Ba2 plus SO42 minus yields what? Barium sulfate, what state? Solid. Okay. Again, I know those are a long time ago, but those are things we have to kind of keep in mind as we go through this. Okay. And the temperature of the mixture increases to 28.1 degrees Celsius. Again, and I said this off the recording, assuming that the calorimeter absorbs only negligible quantity of heat. So what can you say? What does that mean? Just ignore it. Just completely act like it doesn't exist. The specific heat capacity of the solution is 4.18 joules degree Celsius per gram, and that the density of the final solution is 1 gram per milliliter. So Jacob, just like you said, it's important to recognize the volume unit they gave you in was liters, but the density unit they gave you was milliliters. So what do you have to do with both of these liter things? Convert them to what? And guys, I'm going to be honest with you, this is a very, very rare situation. I would say 8 out of 10 times you're converting most of your volumes to liters and not milliliters. So this is a rare case where you actually have to do it the opposite way. And so then it says to calculate the enthalpy change per mole of barium sulfate that is formed. Okay, is everybody good with that? So let's come over here and let's look at what's going on. So we've got Q equals M CP delta T. Now, remember, we're solving for Q of the solution. We'll kind of pause that for a second. The CP was 4.18 joules per gram degree Celsius. Just for time's sake, what was your delta T? Positive 3.1 Celsius, right? Okay, all right, so that's the temperature change. So the problem is they tell you that you have, well, we already just said it. So you know how to do it. What was your total mass? I don't really want to go through that again. It should be 2,000 grams of solution. So again, your Q of solution is equal to what? Okay, so let's go ahead and 25,000 what? All right, so let's do this. So let's do 25.9 kilojoules. Is that okay? Remember, plus or minus 1, so you're good. So positive 25.9 kilojoules, but you've got to remember that we need the Q of the reaction, which is equal to delta H of the reaction. So it's equal but opposite. So what's your final answer? Negative 25.9 kilojoules per what? Per mole of reaction. Now, just like I said off the recording, what happened to the temperature change? It got warmer or colder? Warmer. What reactions get warmer? Exothermic. What is the sign of exothermic reactions? Negative. Was your delta H negative? Good. That's important. What happens if the delta T was negative there? It means it got colder. It means it's endo. The delta H has to be positive. Okay? So does this help? Does this make sense? Here's the last question, and we're going to actually go back to this question because I want to see how much of this stuff you remember. And this is what I want to end with today. It has nothing to do with calorimetry. It has everything to do with stoichiometry. Here's my question. And again, I want to see if you can actually do this. Do you agree you had a reaction going on? And it told you that some white solid barium sulfate was formed. How much? In grams. Calculate it. That's the last thing we're doing today. And again, I'm telling you, you're going to see questions like this. You've got to be able to do stoichiometry. Set up your reaction. See if you can figure it out. That's your goal. It scares me that you're looking at me with blank stares.